Hello, my wonderful students and chemistry lovers. Today, I'm going to talk to you about coordinate covalent bonding, which is also known as dative covalent bonding. My name is Dr. Lotano Okwesili, and I'm going to serve as your guide today in this interesting lecture and conversation, okay? When we talk about coordinate or dative covalent bonding, in this type of bonding, what happens is that the two electrons that represent what we call the bonding pair or the shared pair, which ultimately gives us what we call the single covalent bond, is usually being supplied by one atom out of the two combining atoms. I'll put it in another way. In the dative covalent bonding or coordinate covalent bonding, one atom out of the two interacting atoms usually bring the two electrons needed for the bond formation. And a beautiful example of the formation of coordinate covalent bonding or dative bonding is found when we make ammonium chloride by reacting ammonia and hydrochloric acid. All right? So, of course, using the Lewis structures, you can now see that ammonia, of course, is a base, has a one lone pair of electron, that is electrons that are sitting idle, that was not used for bond formation, which actually can still be used for bond formation. That's what we call lone pair of electrons. So it has a lone pair of electron. Why? Of course, this is hydrochloric acid. Of course, hydrogen obeys the duet structure or the duet rule, in which case it supplied one electron, chlorine brings one electron. So we have two electrons in this covalent bond, one from hydrogen and one from chlorine. So what happens in this reaction is that an acid, according to one of the theories of acid, is called Bronsted-Lowry theory. According to Bronsted-Lowry theory of an acid is a proton donor, while a base is a proton acceptor. Why I just mentioned about the theory of acid is that one of the ways we describe dative covalent bonding for students to appreciate is by closely looking at what we call acid-base reactions. Acid-base reactions are beautiful examples that help us to actually bring home the idea of the formation of coordinate or dative bonding. So again, according to Bronsted-Lowry theory, which is one of the key theories of acid and base reactions, is that an acid is known to be a proton donor, while a base is a proton acceptor. So what happens when you react ammonia and hydrochloric acid to make ammonium chloride is that the acid, which is a proton donor, hydrochloric acid in this case, supplies its proton. Proton is H+. And of course, when something has a positive sign, it means is that it's either metallic, must have given out its electron, or it left its electron behind if it's a non-metal like hydrogen. What that means that, remember, in this single covalent bond, hydrogen ab initio brought one electron, chlorine brought one electron. All right. However, when this is ejected as a proton, it means the 1s orbital is empty, even though it's left with the nucleus or the proton, one proton. So when the proton from this acid has been transferred or shot on to the lone pairs of electron on the ammonia, the two lone pairs of the one lone pair of electron representing those two electrons is enough to make a covalent bond, in which case it actually now makes a covalent bond. But because this covalent bond is being made by electron that belongs only to nitrogen, hydrogen is coming from of a proton. That means in the 1s orbital you have 0 electron, and s orbitals can carry 2 electrons. So the 2 electrons that you use to now overlap with the s orbital of this hydrogen coming in form of proton is what we are talking about, okay? So what we are saying is that, of course, the hydrogen ion now comes and attaches itself here, and that makes a kind of covalent bond known as a dative covalent bond. Dative because we had a lone pair of electron here. That lone pair of electron, when hydrogen ion has been attached, we use that lone pair to make one single covalent bond. But because that lone pair is only from nitrogen, the covalent bond is known as dative covalent bond, okay, or you call it coordinate covalent bond, a kind of covalent bonding where the two bonding pairs or shared pair is only supplied by one atom, in which case nitrogen from ammonia. And to be able to depict to differentiate this dative covalent bond from the ordinary covalent bonds, because already ammonia had 3 ordinary covalent bonds, 1, 2, 3. But it now had the 4th bond. The 4th covalent bond now becomes what we call dative covalent bond. And normally, in simple structures or simple diagrams, we always want to use an arrow, okay, like this to represent or differentiate the dative bond from ordinary covalent bonds. So in ammonium ion, as it is, we have 4 covalent bonds. 3 are ordinary covalent bonds, joining hydrogen, these 3 hydrogen to the nitrogen, while the 4th one that was formed after protonation of the base is known as a dative covalent bond, which I tell you we always depict using an arrow. The arrow is always pointing from, showing where the electron came from, the atom from where it came from, and the atom where it went to. So the 2 electrons that were used to make this dative bonding came from nitrogen. So the arrow is pointing from nitrogen to hydrogen. All right. But because hydrogen came into this particular compound or into this relationship as a positively charged ion, you enclose the ammonium ion that has been made and give them the net charge of plus. That net plus positive charge, you place it outside the box. All right. Remember, conservation of matter. Matter can neither be created nor destroyed, in which case the charge here is almost a matter. If we had charge coming into this, at the end of the day, we cannot do away with that charge without explaining it. So what we are trying to say is that this positive charge that belongs to hydrogen ultimately now belongs to the entire molecule, since it is that the 2 electrons that were used to make bond belong only to nitrogen. All right. How that means that what belongs to the proton, the hydrogen that is coming now belongs to everybody. It's called mutual. The relationship has to be mutual. And ideally, matter should neither be created nor destroyed. Charges should always be balanced. Okay? I believe it's clear. And because hydrogen left its electron for chlorine, that means chlorine now has 1 more electron that made it stable. We now have a chloride ion. And it's important for us to understand that according to the Bronsted-Lowry theory of an acid, what we call a conjugate acid is made whenever a base is protonated. When an acid donates a proton to a base, what we produce from that base is called a conjugate acid. And whatever that was left after deprotonation of acid, that is after the acid has protonated the base or donated the proton to a base, is known as a conjugate base. So we need to understand the 3 key theories of an acid if we must understand acid-base reactions. And in turn, for us to explain coordinate covalent bonding very well, acid-base reactions are very wonderful examples that will help us drive home the point. I believe it's clear. So you can understand that ammonium chloride is formed, and then when after ammonium chloride, which is a conjugate acid that is formed here, in reality, it is difficult for us to differentiate the 4 bonds. All right. Like I said, in simpler diagrams, we just use an arrow to show where the atom that brought the shared pair, all right, which is nitrogen, pointing an arrow pointing towards the atom that accepted it, in which case you have the hydrogen. So what we have here is called ammonium. And of course, what we have here is chloride. So the electrostatic attractive forces holding this ultimately gives us the compound ammonium chloride. I believe it's clear. For us to summarize this reaction, you can agree with me that a base, of course, reacted with an acid. Of course, this is a reversible process. It can proceed both forward and backward, of course, to give us the conjugate acid, as you can see, and to give us a conjugate base. So this equation summarizes this example that we have. So we have 3 key theories of an acid. Again, I've talked about the Bronsted-Lowry theory, which again tells us that a conjugate acid is made when you protonate a base. The proton used in protonating the base comes from an acid. So that is the product of a base that has a proton attached to it is called a conjugate acid, and that a conjugate base is made, or is what is left behind after an acid must have deprotonated or donated its proton to a base. I believe it's clear. Now, we have made ammonium ion, which I told you is acidic. So if ammonium ion is coming now to become a reactant or a substrate on another reaction, we're not going to call it conjugate acid now. It's just going to be called acid. All right. In the reactant side, it's just acid and base. At the product side is where you now begin to have your conjugates. All right, which are resultant products of acid-base interactions. So you can agree with me that ammonium ion, which is this NH4 plus, is an acid. Of course, you've seen how it's made. And according to the first theory of an acid, known as the Arrhenius theory, an acid is a substance which, when dissociates in water, produces hydrogen ion as the only positive ion. Whereas, according to Arrhenius theory of acid and base, a base is any substance which, when dissociates in water or ionizes in water, releases hydroxide ion. So hydroxide ion, according to Arrhenius theory, the first theory of an acid, represents a base. So in an aqueous medium, if you have an ammonium ion, NH4 plus ion, and of course you have OH, this is OH, hydroxide ion. This hydroxide ion depicts the presence of a base according to Arrhenius theory, because according to Arrhenius theory, a base is a substance that dissociates in water to produce hydroxide ion. So of course this is an acid, and whatever it is, sodium hydroxide, potassium, whatever it is that is here that generated this ion in the aqueous phase must be a base. All right. Of course, when you react ammonium ion, react it with hydroxide ion, you are going to, of course, make a conjugate base and a conjugate acid. How? Remember, we protonated ammonia to get ammonium ion. So the way to do this is to deprotonate. All right. Remember, an acid, according to Arrhenius theory, substance which, when dissolved in water, produces hydrogen ion. Of course, in aqueous phase or in aqueous medium, what happens is that of course, it dissociates, it ionizes, and that proton that was introduced, okay, or was transferred from the hydrochloric acid to its ab initio in the aqueous phase, you see that what happens is that the proton breaks away, and that proton, okay, is now fired or transferred onto the hydroxide ion, which is in the solution. Are you seeing it? So here, it's an acid, it's reacting, is now an acid, supplying its proton to a base, okay? And it's also important for us to also know that apart from the Arrhenius theory that tells us that hydrogen ions are products of dissociation of acid in aqueous phase, and hydroxide ions are products of dissociation of base in aqueous phase, again, the Bronsted-Lowry theory told us that an acid is what? A proton donor, why a base is a proton acceptor. So that theory also shows what's going on here. If this is an acid, that means it can donate a proton to a base. And when that happens, when that proton that came in here left and goes to the base, you get back your ammonia. And an acid will produce a conjugate base. All right? So when an acid has been deprotonated, when it has lost its proton, you are going to make a conjugate base. And whatever it was that whichever base or whatever it was that accepted that proton from the acid, which was a base, now forms a conjugate acid. So hydroxide ion plus one more hydrogen, of course, makes water molecule, because you can now see that this hydrogen ion, okay, this hydrogen now comes to make, of course, a bond, makes a covalent bond here. And of course, the oxygen supplied the 2 electrons, okay? And it is important you understand it. The oxygen supplies the 2 electrons. But because we have proton coming to combine with hydroxide ion, the 2 charges cancels out. That's why you don't have a charge, a overall net charge. But ultimately, just know that water here is a conjugate acid. Why, of course, our ammonia, which was deprotonated after being an acid, shooting its proton to the base, becomes a conjugate base. it is important for us to understand that water is a very special kind of chemical. As a matter of fact, water in acid-base theory can behave as both an acid and a base. That's why we say that water is amphoteric. So if you check closely, you see that after hydroxide ion has been protonated by ammonium ion, it becomes a conjugate acid. Here is behaving as an acid. In some other instances, you see water reacting as a base because it is amphoteric in nature. It's an amphoteric oxide. So another example of dative bond formation is seen when, of course, when hydrochloric acid dissolves in water. So here is an acid, HCl in aqueous phase, and of course we have water. Water here is now behaving as a base, okay? And when that happens, you are going to make what? A dative compound called hydrozonium ion or hydronium ion or ozonium ion, and of course you are going to also produce chloride ion. So if we use the Lewis structure to depict this, this is the Lewis diagram for hydrochloric acid, this is the Lewis diagram for water. What happens again is that the acid is a proton donor, so it supplies its proton here. Are you following? Of course, because the oxygen has 2 electrons that he has now used to make a bond with this particular hydrogen that is coming from the proton. Of course, you now have your dative bond showing that the 2 electrons that join hydrogen to oxygen came from oxygen. So you see the arrow pointing from where the electron came to this. And because proton again is coming with a positive charge, we place the entire molecule in square brackets and put a net positive charge over it. So here what we have made is we had oxygen attached to 2 atoms of hydrogen, but now we have another hydrogen coming to make a bond here. We now have 3 atoms, okay, hovering around the oxygen atom. So this is no more water, rather this is called hydronium ion, or you call it hydrozonium ion, or you call it simply an ozonium ion, H3O+. As a matter of fact, in aqueous phase, you will never find, in the aqueous media, you will never find hydrogen ion, moving around as just a single species. Most times, hydrogen ions protonate water, and in the aqueous phase, you see them moving around in form of hydronium or ozonium ion. And because you can see chlorine, hydrogen left chlorine with its own electron because it's a proton. That means that, again, chlorine has 1 extra electron that helped it to attain its octet. So chlorine becomes chloride ion at this end. So the oppositely charged, the electrostatic attraction between the oppositely charged particles is what holds the compound in place as it is. All right. So this is beautiful. Another example of dative covalent bonding is seen when you react ammonia with boron trifluoride. Boron trifluoride is one of the exceptions to the octet rule. Refer back to our video when we were talking about drawing Lewis structures. You will discover that boron always wants to make 3 single covalent bonds. It's an electron deficient molecule. All right, it forms electron deficient molecules. However, if there is still electron from somewhere, maybe a lone pair of electron, it can actually make up to 8 electrons. That's 4 bonds around it, which is what we will see here. All right. So if you react ammonia gas with boron trifluoride, which is of course a very toxic gas, we are going to make an adduct known as ammonia boron trifluoride. In chemistry, an adduct is a particular product or a chemical compound that is made by directly adding 2 distinct molecules to make that single product. You see, here you have ammonia, distinctively a basic gas, and here you have boron trifluoride, distinctively a very toxic gas, okay? And when you combine both of them, you're going to make ammonia boron trifluoride, which is known as an adduct. An adduct, okay, is made by directly adding 2 distinct molecules together. This is what we know as adduct in chemistry. So here, let's use the Lewis diagram to appreciate what's going on. Of course, ammonia again, which is a base. Remember, ammonia is a base, but here it has 2 lone pairs of electrons. And of course, you have your boron trifluoride, I told you, usually makes 3 covalent bonds with hydrogen. All right. So what happens again is that for us to appreciate it, we've briefly talked about the Arrhenius theory, which tells us that acids ionize in water to generate hydrogen ion, base ionize in water to generate hydroxide ion. We also discussed about Bronsted-Lowry theory of acid and base, which says that acids are proton donors, and of course, bases are proton acceptors. Now, the third theory of an acid will help us to appreciate what is happening here. It's known as the Lewis theory. In the Lewis theory of an acid, a base is an electron pair donor. A base is something that carries lone pairs of electrons, which is able to donate to an acid, which is an electron pair acceptor. So according to the Lewis theory of acid and base, a base is a proton electron pair donor, while an acid is an electron pair acceptor. So you will agree with me here that this is a base because, of course, it has one lone pair of electron, that's 2 electrons to donate. And of course, this is an acid because it has the capacity of accepting that 2 electrons donated by the base. So according to the Lewis theory, a base donates a pair of electrons to an acid, and an acid accepts that. And that is what actually happens here. Remember, we said that boron makes electron deficient molecule. That means that normally to want to make 3 covalent bonds around it. However, if there is still, a lone pair of electron from some other way elsewhere, we can use that to make the 4th bond around it, which is exactly what happens here. So what happens is that this lone pair on ammonia is transferred or is shared. Ammonia shares it with boron. Oh, boron, since you are electron deficient, okay, come, let us join up and share my own lone pair of electron so that we can make a covalent bond. As you can see, the arrow again showing this, depicting this coordinate or dative bonding, shows that the 2 electrons used in making this covalent bond comes from nitrogen and was shared to boron. At the end of the day, you see, ultimately nitrogen has 8 electrons around it by way of 4 covalent bonds, and of course boron has 8 electrons around it by way of 4 covalent bonds, 3 being ordinary covalent bond, joining boron to 3 hydrogen atoms, and the 4th one being a coordinate or dative bonding, joining boron to nitrogen. So again, you can say that nitrogen have 4 covalent bonds, which are 3 ordinary covalent bonds joining nitrogen to 3 hydrogens, and 1 dative covalent bond joining nitrogen to what? To boron, as it is. So you see that the third theory of an acid helps us to understand what led to the formation of this adduct known as ammonia-boron trifluoride, in which case we had a base being an electron pair donor, transfers its electron pair and shares it, of course, with an acid, which is electron pair acceptor, and of course we make ammonia-boron trifluoride, which is an adduct. An adduct, again, is made when you have 2 distinct molecules directly linking up, of course, to make a beautiful distinguished compound known as an adduct. I believe it's clear. So you see that in the last lecture video, we talked about ordinary covalent bonding, where the 2 combining atoms each bring 1 electron. But in coordinate covalent bonding, the 2 electrons for the making of the covalent bond comes from only 1 atom. I believe it's clear. But this is not the full story. The full story is that in some other instances, atoms can combine by bringing either 2 electrons each or even 3 electrons each. In that case, we now begin to talk about multiple bond formation. All right. If 2 combining atoms bring 2 electrons each, they make what we call a double covalent bond. And if the 2 combining atoms supply 3 electrons each, they make what we call a triple covalent bond. Okay. So this is what we've seen in the formation of a ethene and the formation of a ethyne. So in the formation of a ethene, of course, carbon will always want to make 4 bonds around it, whether by way of 4 single bonds, okay, or 2 single bonds, 1 double bond, or 1 triple bond, 1 single bond. Whichever way, carbon always wants to have 4 bonds going out of it into a nearby atom. So here you have 2 atoms of hydrogen already attached. So what happens is that, of course, if this Carbon supplies one atom, and of course, this carbon supplies one atom. They make a covalent bond, one under. Again, if this supplies its electron and this supplies its electron, that means they brought two electrons. They make the second covalent bond. Okay, so here you have a double covalent bond. So ultimately, you have 1, 2, 3, 4 bonds around this carbon. Of course, this double covalent bond is also for this guy. So ultimately, you have 1, 2, 3, 4 covalent bond. So in which case, you now have what we call double bond. A double bond is formed when the combining atoms each brings 2 electrons, as you have seen in a tin. All right. Again, in some instances, like you see in the formation of a tine, each of the combining species brings 3 electrons. So you see that this guy can, of course, bring one of its electron. This brings this electron, makes one bond, the central bond. Of course, this brings one of its electron again. This brings one of its electron again, makes another one bond. Of course, there's still one possibility. This brings one of its electron, and this brings one of its electron, and completes the bond, joining carbon to be triple. So we have multiple bond formations. All right. So when we are talking about using one atom supplying 2 electrons in coordinate covalent bond, in some other instances, the 2 combining atoms can actually supply the 2 bonding electrons, and that way we make a double bond. The multiple type of bond here made is double covalent bond, which is stronger than single covalent bond. However, it's also shorter than single covalent bond. I'm going to talk about that in some other video. All right, I believe it's clear. And finally, when you have the 2 combining atoms, each supplying 3 electrons, you have a triple covalent bond. I don't know if you learned anything in this lecture video, but if you learned anything in this lecture video, kindly give me a like, a love, make your comment, and share this video so that it can get to some of the students who need some of the information we are dishing out today. Kindly subscribe to my YouTube channel on Chem Class with Dr. Luther. Invite your friends to follow our page here on Facebook on Chem Class with Dr. Luther. Let's continue to make chemistry easy and fun to learn. It doesn't have to be fight, okay? As much as lie within our power, we're going to be bringing chemistry so that our learners and chemistry lovers will continue to upscale and make their chemistry better and better every day. I believe you learned something. Until the next time, I remain your humble friend, Dr. Luther Nokwesili. Stay safe and stay away from trouble, okay? Bye.